So this is definitely a really long presentation, and it took us a couple hours to get through it. So I'll probably just be kind of skipping over it and focusing on the main points of it. Um, so, like you mentioned, we are an international team. So we are associated with 3 other universities. Um, so here at CU, University of Colorado, we are responsible essentially for the embedded systems design of the project. So we're making everything that essentially goes inside the aircraft, whereas University of Victoria is responsible for the airframe design and the actual fuselage housing of the payload that we're going to be designing. Metropolia University is located in Finland, and they are responsible for the ground station network. So on top of the aircraft, we're going to have a ground station network, and they are responsible for building all of the ground station network communication systems that communicate with us. And then University of Stuttgart is actually located in Germany, and they're responsible for the design of the wing and empennage system. And they actually just sent a representative out to University of Pretoria in South Africa and have fabricated the wings. So that's kind of where they're at with that, and they are planning here on hopefully making a test, putting together the fuselage and the wings and empennage, and doing a test flight of the aerodynamics of it. So they've actually fabricated the wings and done a wing loading testing on it, and so far that has it worked. So it withheld the loads that were put on it. So our whole project kind of has 2 aspects to it. So we have a long-term goal and a short-term goal. So our long-term would eventually be to create these sectors in Kruger National Park, seen here in red. And essentially, we have a ground station and an aircraft in each one of those sectors that could essentially patrol up to, with a reach of 30 kilometers, into these sectors and patrol for poachers. And essentially, this is how each sector would look. We'd essentially get a target of interest in mind, and we would launch from our launch station, fly out to our waypoint that we've programmed, and then we'd do a search pattern essentially, all while communicating with our ground station, and then return back to our launch station. So that would be our long-term goal. We realize that this is kind of a lot to do, so we are actually in a phase A demo. Let's see if I can minimize this. There we go. So this is actually the aircraft that we'd be designing. So it is a pusher prop, and then we have an actual reverse V-tail for our aircraft. And then the fuselage is kind of a fat body fuselage. Do you guys kind of have any questions so far about what I've described?
What's what's the flight time that you guys are aiming for with this particular model?
So our long-term goal would be 90 minutes. But we've actually, so that's part of the reason is that we've done this phase A demo flight, because in order to get a super light aircraft, we'd have to do some molding on the wings and the empennage, and we actually didn't have the budget for that. So this demo flight is kind of more of a proof of concept. And since the wings that we fabricated are heavier than what we would like, we're not going to get the 90-minute endurance that we would like. So for this flight, we're essentially going to do a 15 to 20-minute flight, just basically proving that our ideas work. And then we'd like to move forward and actually do better fabricated wings, improve the weight of it, and then hopefully get our 90-minute flight time out of it.
So one thing unique about your team is that not only are you guys focusing on like the embedded systems for the challenge, but you're actually creating your own aircraft in the process of it as well. So, and I see that you have such an amazingly managed team, because how many team members are there total, roughly?
So there's 11 on the University of Colorado side, and then there's so we have a lot of volunteers all throughout the universities, but we have about 4 consistently working through South Africa. About there's actually 1 main guy working on Metropolia right now, because they've actually almost completed their design of the ground station network. But there's also a lot of volunteers that they have working there, and then there's about 3 that are working on the wing and empennage in Germany, because they've already pretty much finalized their design. So they just are really without 1 person in South Africa right now. He's still working with them on assembling it. So.
Oh, that's pretty good.
Mm-hmm.
A lot of managing overseas and time changes and everything. So it's pretty
Yep.
interesting that your aircraft is going to be made in so many different countries.
Mm-hmm. And so right now we're actually mainly focusing on the embedded systems part of it and the fuselage.
Okay.
So
I know you mentioned
and
that,
also the propulsion.
and then you said that recently you did some tests for the embedded systems, right? And you're going to talk about those more in detail.
Um, Arend can probably
Okay.
talk about those better than I can.
All right. Well, do you want to go ahead and continue with this, and then we'll break for questions in about I guess 10 minutes or so.
Okay, sure. Um, so I can go into let's see. We have a lot of I'll just go into the system overview essentially. Um, Yeah, so essentially our long-term goal is eventually we'd like to get to the point where we've essentially created a cyber canopy. And so that includes, we would like to have a ground station set up, which is actually what we're working on right now, and of course the air system. But eventually, we would really like to see this project go into a full canopy that has towers stationed, so that we can get greater distances of communication and satellite if possible, so we could essentially create a fleet of aircraft. So that would be one of our very long-term goals, but we are very excited to possibly pursue this opportunity. And so here's more of how our aircraft is laid out. So what we have a visual camera and an infrared camera that's connected to a gimbal system, and that will be on the front of the aircraft. And that will be communicating with a CPU, which is actually an NVIDIA processor. And so we'll be using that to do onboard processing of the images. And in this demo flight, we'll actually be storing those on board and processing after. And then we have an autopilot system, which is the Pixhawk, if anyone is familiar with that. And one of the key things that we have in our project is we have a section for variable payload. So that is something that we really want to focus on, and I think that puts us apart from other UAVs that are trying to prevent rhino poaching, is because we would like to get to a point, and we've designed a few variable payloads that we can put into our aircraft. And so this essentially would be if we are, so we get to the park and someone has an idea for another sensor suite they can essentially put in the aircraft that we haven't designed for. So, for example, someone we've talked to has what's called a smell sensor. And it essentially is a very sensitive sensor to molecules in the air. So essentially we could say, look, we have this much room in our aircraft that we have available for a payload. So they could say, okay, we'll give you this payload and you can put it in your aircraft, and then say if someone poisons a lake with cyanide or arsenic, like some poachers do, we could essentially have the aircraft dive near that lake and sense if there's arsenic or cyanide in the water. So that is something that our advisor, Dr. Koster, has really stressed in this project, is getting a variable payload option for this aircraft. And so that essentially would just allow us to not limit ourselves on what this aircraft can do, but just always get in new payloads inside it if need be. And then this is kind of just data flow. I don't feel like this is very necessary to go into. It's just pretty technical. So I'm going to go ahead and skip over that. A lot of this presentation is technical, so I don't want to go into too much technical details. So maybe I'll actually go back to this picture because I forgot I didn't talk about a few things. So we will be transmitting data to our ground station network. And so we'll have a transmitting antenna and a receiving antenna, and we're going to go ahead and put those in the wings. Of course, we'll have our propulsion system, and that actually is one thing that, like I mentioned, made us scope down our project a little bit, is that in order to get a 90-minute endurance, we have to have a lot of batteries, and it just adds a lot of weight. So that's another reason that we scoped down to a shorter endurance in our demo flight, but we'd like to increase that later, is because of the batteries we need. And so that's, we actually have, the batteries would be up here and distributed through, we have a whole power distribution system that would distribute it to all the embedded systems on board. So I'm going to go ahead. This is essentially just component selection that I'm skipping over. And then, Aaron, I don't know, do you want to talk about the Autopilot a little bit, since that is a big part of the project?
I don't think we need to go into too much technical details on it.
Okay.
Maybe just kind of show the slide 68.
68. Okay, yeah, that I was just thinking about like the waypoints and stuff like that.
Great. So one of our ultimate goals in designing the embedded systems is to make this usable for the end user. So the Autopilot we're using comes with a ground control station, which is a mission planner. So the image on the right, it overlays the current location of the aircraft on Google Maps. And then on the left, it'll display a bunch of information that will be important to the pilot. One of the biggest features of this is that you can't just click on the Google Maps and tell the aircraft to fly there. You can tell it to point the camera gimbal there. In the long run, this capability will be used to allow the operator on the ground to visually verify sensor input. So if a sensor detects that someone is within a certain area, you could then click on the map and have the camera point at that location just to verify that it is actually a poacher in there. Like Ethan said, it's kind of sorry, I don't think there's too much else to go into detail here.
Mm-hmm. We're essentially just, this is part of the testing that we've done. Aaron's essentially done a few experiments with this simulator, and essentially we've been working a lot on, or he's been working a lot on, figuring out how the autopilot works and how we're actually going to navigate this thing in flight. And that is one thing, is we're actually going to do a manual flight in this demo flight, just because we're not sure how the aircraft is going to react with all of the weight distribution and the aerodynamics, and we just don't want to push it too much in this first flight and accidentally crash it. So we are going to be doing manual control.
So are you guys using Mission Planner as your ground station, or are you playing with any other ground stations as well, software?
Yes, we're using Mission Planner.
Okay.
So, and then we'll jump into a little bit of the housing of the aircraft. So this fuselage is what Pretoria has designed, and it essentially has a rod running through it, as you can see in the picture here. And that rod is essentially what we're going to be mounting all of the components to. And what someone has done here at CU is they've designed these two plates that you can see here. One will be for mounting batteries, and the other will be for mounting our variable payload onto. So currently this is what the battery design, looks like. Is it'll essentially have this case where all the batteries that we have can fit in, of course with windows looking through it, where all the connections can be made. We have done some analysis on this to see if it will hold, but I don't feel like that is super important either. I'm actually trying to find here our variable payload. So this is one thing that we were talking about, how I said it was important. What Dr. Koster wanted us to do is create this variable payload aircraft. So we've looked into a few options, and one of them is the RFID integrator, and so that would essentially be we could integrate this into the aircraft and say maybe it's a more private part, and they tag their rhinos. We would be able to fly our aircraft around and figure out the location of those rhinos based off of this RFID integrator. Another one would be detecting mobile phone of a poacher. So that's one thing we've looked into. And another is, of course, that smell sensor. And so we would like to keep those confidential, as we don't want them getting into the wrong hands of how our design would work. So it is important that that information is kept private.
Hey Ethan, there are a couple of, there's a comment and then a question from Elmar. Elmar said that you should consider skipping Google Maps because they don't have internet. I'm assuming he's talking about in the parks, and you will run into some problems that way.
And so I think, Arend, do you know more about what the ground station network is doing?
So I think what you were referring to is for loading the Google Maps. We can do that ahead of time in a location where we have Wi-Fi access.
Okay.
And then it will save all that data up to the laptop to be loaded during the actual flight.
Okay. And then we have a question from Michael on, are you using any Python scripting on the Pixhawk?
Yes, we'll be using it on the onboard flight processor, which is that NVIDIA. That will be on the aircraft and essentially acting like a ground control station. So in there, we'll have Python scripts which will interface with all of the sensors, and they can send telemetry, or they can send control commands to the autopilot in case something is detected, or if we have thermistors running too hot, or whatever it may be. So there will be Python scripting, not on the Autopilot itself, but on a separate flight processor.
Mm-hmm. So, and I think that is the general overview of what we've accomplished so far. Of course, we do have a lot of technical aspects in this presentation, so if someone would like to know more technical aspects about the processor or anything like that, we can definitely go into that. But I feel like it would just be a little too much to go in depth into the technical aspects.
We can ask, I mean, if anybody has any specific questions, they could definitely ask about that. Steve, I guess you've got a question. I can't hear you, Steve. Are you? Oh, wait, hold on. I think you're on mute. Sorry, go ahead.
Great. Tell me, the part that always gets me quite interested is what sort of communications are you using between the ground station and the aircraft? How do you plan to stream video? What sort of protocols and networks and things like that are you creating to control and manage the aircraft, and also to get the data down to the people that matter?
I can definitely go into that. It is definitely not my area of expertise, but I can tell you as much as I can.
I'll give you a quick overview on that.
Sorry, what was that, Aaron?
I could go into just a quick overview on that.
Okay. Yeah, I'll just pull up this slide here.
So for manual control, we just have your hobbyist RC controller, so to fly the plane in manual control. For Autopilot, it's a little bit more complicated. We're using a 2.4 gigahertz serial radio that we were purchasing from a local company here in Boulder. One of the most important features of this radio is the encryption. So we'll be using full 256-bit encryption on all of our telemetry data. So all the GPS information will be encrypted, where our aircraft is at all times, and any sensor data that's coming down. So,
and what sort of range do you expect to get with the system?
With our manual control, we recently tested that and got a range of about 20 kilometers. So it's very dependent on line of sight. So we have one case where we went over a hill and lost the link after about 10 kilometers. Yeah, and then we went in a different direction. We're able to get about 15 to 20 kilometers. So we've not tested
radio line of sight. You're getting up to 20 kilometers.
Right. We haven't tested the telemetry link yet, and that's on our test plans for the end of the semester, though.
Are you using any sort of directional antennas?
Not for the short-term stage, we aren't.
Okay.
It would have required an antenna tracking base, which is just out of scope of our project. It is in our long-term design, though.
Okay, okay.
We have a question about do you use any computer vision software?
So in the demo, we will not be. On the flight processor, the plan is to use image processing to detect the either rhinos or people in the park with the high resolution camera. And that's work being done by the University of Pretoria. But they are going to be using test images from our test flight to develop that algorithm.
We have a question from Elmar. What will you be processing on the NVIDIA CPU?
So the NVIDIA, like I said, is for the image processing. So the camera will be sending its images to the NVIDIA. In the short term, we're also kind of using it as a onboard battery manager to interface with our state of charge detector. We also have several thermistors that are going to be wired into the NVIDIA just to make sure temperature on all the components are okay.
And so that is one thing that we wanted to monitor is one thing we were very concerned about is actually crashing in the park. We definitely don't want to start any fires or anything like that, or of course damage the aircraft. So that is one thing that we've programmed into or we'll program into the NVIDIA processor is basically a state of health monitor system. So if the batteries start getting too low, we have a state of charge monitor that's going to be monitoring those batteries. And if they get too low, it'll essentially tell us to turn back and return to the launch pad. Also, we'll be monitoring heat, which was one of the major concerns that we had, and that's, Aaron mentioned we had thermistors that are essentially going to be taking the temperature of the aircraft. And if that gets too hot for our sensors or starts approaching that limit, once again, we'll turn around and return to the launch pad. And that is something we can program into the Autopilot, is essentially a return to launch protocol. One thing we are doing to avoid the heat is putting vents into the fuselage and fins so that we can dissipate that heat easily, because we know heat is going to be a major concern, especially in the park. So.
Okay.
Ethan? Oh.
Go on, Steve. I'll just.
Ethan, your craft, is it, what sort of landing and takeoff configuration do you require? Or, yeah, tell me, what is it, what sort of mission in terms of landing, takeoff, and emergency landings and things like that? How will that work?
So this is something we actually didn't include in this presentation, but I can talk about because it's actually something that the University of Pretoria has been working on. And essentially what they're doing is they're creating a landing skid for the aircraft. So it's essentially, let's see if I can get to the picture of the aircraft again. So it is essentially on the bottom of this fuselage, and can you guys see my mouse, by the way?
Yeah.
Okay, so it's on the bottom of this fuselage here, and it's essentially just a single skid that follows the curve of the fuselage, and when we want to land, it basically essentially extends out, and will be a skid under here. And that is one thing we've had a little bit of concern about is, of course, if we're using a single skid, we're going to have to be very balanced in the aircraft so as we don't tip and essentially break a wing when we land. And so that will be reinforcing the tips of these wings and ensuring that we're balanced so that when we land, it's a clean landing. As far as emergency landings, we do have a parachute implemented in the aircraft, and essentially what will happen is this red nose will pop off of the aircraft. It'll still be attached, but it will pop out and hang, and then the parachute will deploy out this way, and then they'll both just fall to the ground. So that's our emergency plan. Ideally, we would not want to use that because it would rip out connections to our camera system in here. So we ideally would want to use that, but that would be an emergency case where we needed to land or something was failing. So.
And your takeoffs?
Takeoffs will be, we'll have a, it's a little ambiguous right now. It is something we'll have to work on, but what we've mentioned is a rail or a cart, essentially. And I think we're leaning towards the cart option where we essentially have a cart that we place it on. It gets up to speed on this cart with wheels and then takes off.
We have a.
And
Sorry.
Sorry, go ahead.
Obviously your craft is totally composite. Is that right?
Totally what?
Composite, of composite construction.
So long term, yes. The fuselage will be composite, but the wings and empennage, I believe, are a hard foam at the current moment.
Okay. Okay.
Kamel wants to know. He's with Dutch UAS. Where are you guys doing your test flights, and if you would be interested in collaborating on sharing videos, because they have a lot of videos, especially in South Africa.
Yeah, we would definitely be interested in that. So right now, we are planning on test flying in South Africa. So we did have a little bit of a schedule conflict and originally wanted to get a flight in before the end of the year. But we do have a lot of manufacturing and testing to do, so that's probably going to be earlier next year. And what we're doing is we're actually, one of the persons at South Africa is actually a pilot, and I believe he has access to, I don't know if you know more on this, Arend, so feel free to jump in if you do. But I believe he has access to a facility where we can fly that is similar conditions to Kruger National Park. So we will be shipping out our components to them in South Africa. They'll be integrating the embedded systems into it and then doing a test flight there. We would definitely be interested, though, in sharing those videos with anyone that wants it. So.
Okay, cool. And then Michael wants to know if you guys would be, if you could go through some more of your slides, because you've got some interesting stuff. And then also, what is the wingspan for your aircraft?
Yeah, so I believe the wingspan, Arend, do you know what it is specifically?
Last I had heard it was 3 meters.
Yeah, that's what I was thinking. So, that is something you are not actually working with directly here. So that's Germany.
Okay.
But that is the last I heard too, is around 3 meters. So.
Okay. Elmar's got a question. Why are you using such a powerful processor, and why are you not using something more real time for these tasks?
Mm-hmm. So Arend can probably go into a little more in depth in that than me, but one of the things is we originally had a BeagleBone processor, is what we wanted, and that actually didn't have the processing capability to process the images that we wanted. And one thing we had been recommended by South Africa is to look at the NVIDIA for the long term. And so it basically did come down to processing power, was the bottom line, is that in order to process the images we were getting, we needed a more powerful processor. Okay. Is there anything you'd like to add, Arend?
No, that covers it.
Okay. Yeah, so we did originally have a different one, but it wasn't actually working for us. So.
All right. And then Camille wants to know, who should he reach out for video sharing?
So you can reach out to me, and I'll take care of that. My email is just ethan.long@colorado.edu. So if you just go ahead and send me an email, I can also coordinate with our advisor, Dr. Koster, and direct on video sharing. So. So I know more slides were mentioned.
Oh, right. There's another question for Michael as well. What materials are being used in the wing structure?
So that actually is something that I do not know, since it was
in the short term.
Yeah.
Sorry, Ethan. In the short term, we're using like a foam material that it's a pretty solid, heavy foam material, and that was just for rapid prototyping to get the wing built quickly. In the long term, we're going to be moving towards fiberglass to have it a little bit lighter. The main reason we didn't do that for this flight is that the manufacturing process was rather expensive for it.
Mm-hmm. And that actually, so one thing going along those same lines is, since we are using the foam material in this prototype, it actually eliminates, we were originally planning on using space inside the wing to store components. So that is another reason that we're not going to reach our 90-minute endurance, is because we're going to have to run wires on the outside of the wing instead of on the inside, which of course is going to add more drag to the aircraft. So that is something we have to work with for the demo, but ideally in the long-term fiberglass wings, we wouldn't have to do that.
Steve?
No questions right now. I can have lots of questions, but I've got to give other people a turn.
Well, we're open for questions right now. I think I've pretty much asked all the questions that I had in my question box.
What is your sort of projected all-up weight, Ethan, for the craft?
The weight?
Yeah, the all-up weight, you know, with sensors and that sort of thing.
So I believe, Aaron, was the payload weight 18 kilograms, right, is what we'd like to reach?
The wings are designed to carry up to 20 kilograms. We're limiting the weight of the entire aircraft with payload, sensors, and everything to about 18 kilograms.
Mm-hmm.
Okay, and what are you looking at, sort of 2G performance in terms of bank angles and that sort of thing?
I'm not sure what those values are off the top of my head. I think Pretoria's been working more on that aspect.
Okay. Okay.
So we can definitely, if you want to send a follow-up email to me on any questions regarding the wings, because that is something that we definitely don't have a lot of knowledge of, because they actually designed those, as I said, in Stuttgart, Germany. So if you want to go ahead and send me follow-up emails that you have about questions like that, I can definitely get you an answer back. But Aaron and I probably aren't the best resource for those questions. So.
We have a question from Michael. Has any CFD work been done?
No, we haven't done CFD work.
There has.
Has there?
Stuttgart did CFD work on the wings themselves. There has not been any CFD on the integrated fuselage and wing structure.
That's right. That's right. So, and that is one reason we'd like to do a flight without the embedded systems in it, just so we don't harm those components if something does go wrong.
Very good.
Ethan, what sort of speeds are you planning to operate your craft at? You know, sort of landing speeds, takeoff, stall speeds, perhaps cruise, loiter. I'm not quite sure sort of, you know, what your mission profile is.
So I don't actually know the takeoff and landing speeds, but our cruise speed would ideally be, I think it's 90 kilometers per hour is what we'd be aiming for. And so that is one thing we want to test, that we're actually going to test here soon, is the power of the propulsion system we have. And we're actually using a 5-blade propulsion system right now.
That's interesting. Where do you get those? Where do you get those propellers from?
So we actually got the propellers from, I forget the name of the site, but they are 18 by 13, I believe, off the top of my head, and then they're folding blades. So that is one thing that we're going to have to design, is a 5-blade folding propeller hub.
What are you going to make it out of? What materials?
So the hub, I believe, we're making out of aluminum.
The propellers?
The propellers are carbon fiber.
Okay.
And so we're not actually manufacturing those. We did buy those.
Okay. I think you were going to do some more slides.
I can go into, so most of the slides that we have are just technical. So I can kind of skim through them, and feel free to stop me, I guess, at any one of them that we want to cover more in depth.
Just a question, Ethan, just just to interrupt you there, not too much, but you talked earlier about making air vents and that sort of thing to aid your cooling and that sort of thing. How are you going to deal with rain and that sort of thing in terms of that, your additional cooling that you talked about?
So that actually is something that was brought up in this presentation that we are trying to, it's something that we didn't really think about and something that we have to think about now. Ideally, we would not be flying in like pouring rain, but we realized that in Kruger National Park specifically, the weather's pretty unpredictable. And so if there's like a 30% chance of rain that day, we don't want to say that's a no-flight condition. So we are going to try to design the vents, whereas they aren't, they don't allow rain to easily get into the fuselage. We of course don't expect to make it completely rainproof. So if it did start raining while we were in flight, that would cause us to return to the launch. But we would expect to be designing an aircraft that can handle the rain that it will experience in that little time. So.
Now, I must say your aircraft's quite fast, so you can probably get a speed gets you out of lots of trouble.
Yep. So that is one advantage that we do have.
Yeah.
So. And then, so yeah, just going through some slides. We did do some vent analysis on essentially determining if we needed a vent. This was actually pretty difficult because it came down a lot to the coefficient of heat dissipation, which we actually, you can only really experimentally get. So we actually ranged our values and essentially went with our worst case scenario as far as the coefficient of cooling and how that would determine the vent we needed. So we decided that we needed a vent of approximately 12.5 centimeters.
Okay.
We can actually go into some of the risks. I feel like that's a good slide to go over. So one of our top risks are over-discharging our LiPo batteries. We are going to mitigate that risk by having the state of charge sensor that will be constantly monitoring the batteries. That way we don't over-discharge them and experience problems on recharging them. We also have considered electromagnetic interference. We know this is going to be a problem for our communication system. So we are actually designing a Faraday cage for those components. It's a design that we still need to pursue further. We've looked into meshes, and those actually are very frequency specific. We feel like the interference we're going to experience is going to be more noisy. Therefore, that's probably not going to work, and we're going to have to create essentially a box around the components that will be a Faraday cage. And that's going to be a problem for overheating once again. So we're probably going to have to put fins on top of that box that are directly in the flow of our vents. We also have, we talked about components overheating, and we're going to have a vent for that. We just addressed the humidity problem that we are addressing, and then one thing is we do have unknown current draw from our servos, but we have prepared for the worst case scenario that we think servos typically draw. on an estimate for those, and then we'll experimentally confirm our estimates for those. Yeah, so our budget, like we said, is 18 kilograms. Currently, we're at 13.86, which is good, but we do need, we are keeping in mind that this demo is going to be a heavier aircraft, so we expect to get some unexpected mass differences there.
Michael has a question. Is the Qmax the maximum power absorbed?
Let's go back. So the Qmax is I believe it is the maximum heat that we will be generating from our system. And so what someone on our team did is they went in and found all the heat dissipation from all the components we use, the maximum heat that they would be outputting, and put those, and that's what Qmax is, I believe. And then the Q nom is what they'll nominally be outputting. So. And then let's see, a lot of the rest are any of the component selection we had. So maybe before I go into those, does anyone have any questions about the specific components we're using and how we selected them or anything like that? And maybe while I'm waiting, I can just go through some of them. So we have our processor, we have our long-term camera that we'll be using, a solid-state drive for storage. This is our short-term camera that we're using for image capturing, and an infrared camera that we're using. We already talked about the RFID integrator. Of course, the Pickhawk Autopilot. This is our radio, the Freewave GXM, which Arend already mentioned a little bit. Snoopy was the cell phone detection, and of course their misters for heat monitoring. So does anyone have any questions about specific components or component selection?
The Fleet, I think it's Fleet 3. Is this an astronomical camera?
This one, the Fleet 3?
Yeah.
Arend, do you know anything about that?
What was the question again? Sorry.
If it's an astronomical.
I'm not sure entirely what that means, I guess. In the context of
Michael, can you clarify your question a little bit, please? What do you have you guys already tested the cameras out, or you have not? Oh, he said is it used for low light conditions?
Oh, this camera is not.
Okay.
We have a separate infrared camera, and then our viewfinder camera has a very good box rating for low light conditions.
I'm trying to find that camera.
What sort of lenses are you planning to put in your cameras, Ethan?
Actually,
from a focal length perspective.
I believe we're doing stock lenses. Is that correct, Arend? Just what they came with?
Well, no, I think on the slide above the one you're on, like 52.
Okay.
So we're more sizing our lenses based on the resolution that we'll get on the ground. So we're looking for a certain number of pixels on the target and a certain distance between each pixel frame. So, and then the focal view kind of falls out of those calculations.
Okay, yes. No, I was just asking the question really just to try and give everybody else a hint as to what sort of, whether you're using an 18mm or 21mm uh, lens, so that But obviously, it depends on the pixel size of the pixel density as well as the height above ground and and the competition rules.
We actually will have one of the lead researchers for cameras from FLIR doing a webinar for us. I'm working on scheduling that. It's either going to be before December 12th or it's going to be the first week of January.
Great. Yeah, if you could send us an email once that's finalized, I think we'd definitely be interested in attending that.
Yeah, that's going to be a really helpful one for pretty much all the teams that are looking into it. So we are going to be getting, for our research purposes, 2 Tau 640s, one with a 25 millimeter and one with a 35 millimeter lens, which will be available for the counterpoaching games as well for the teams that are looking at using that.
Okay, great.
All right, so if we have no questions, we can call it a day because it is almost 3 p.m. my time.
So,
how
are there
have
any
you guys
last-minute questions?
Yeah, how have you guys enjoyed working on this project?
It's been a lot of fun. I'd say one of the most rewarding aspects is actually working with an international team. It definitely makes it a challenge, but it's actually really enjoyable to hear different lifestyles and talking to people and just how things are done differently between, here in the States versus in South Africa or Finland. There's just those minor differences that are really enjoyable to find out about how things are done. So I'd say that's been one of the most rewarding, and also just the fact that you feel like you're doing something to help make the world a better place. For me, that's been one of the best parts of the project, is that I love the fact that I can use engineering to make a difference, essentially.
Yeah, that's kind of cool. Michael says, great presentation, and Elmar's got a good question for you guys. How are you guys handling the delay in the challenge or the counterpunching games, considering it might be your last year of school?
We've been taking the opportunity of the delay to do more testing, to be honest.
All right,
good. Better system and test more of our components before we actually fly. But
yeah, I think
so that is it. We're trying to make the best out of the situation and just doing as much testing as we can. So
it's definitely working out. And I guess, like you said, it's giving you guys an opportunity to really work on some of those areas, especially since you are a multinational team, and getting some of the parts from one country to another could be as equally challenging. So
yeah, and that is one thing that I'm actually working on right now, is all the ITAR control regulations and getting those worked out, which is not the easiest. So
I guess since you do have some teams that are not in the U.S., are you able to work with them with some of the things that are ITAR controlled for the U.S., but because your team is international, you still abide by those rules?
yeah, so one thing that we're establishing now is I think it's called a strategic trade. I always want to say agreement, but I feel like that's not the right word. But it's essentially, since it's used for educational purposes, that helps us get around a lot of the regulations.
Yeah, that's true. Well, very good. Great presentation, that's for sure. Thank you so much, Ethan and Arend, for your time today. And both of you will be at the AIAA SciTech conference to present for your team?
I'll be presenting.
Oh,
yeah, Arend will be. I don't think I will be.
Okay. Well, Arend, I'm looking forward to meeting with you in that case.
Same here.
Yeah, I think it's super exciting because first we were given an opportunity to just submit a paper, and then they allowed us to have our own panel session, which is super awesome. So we'll have your team and 2 teams from India and then a team from Texas at the conference. But now we've given an extended privilege of actually being able to let the rest of the teams that aren't going to be able to make it to the conference submit their team posters. So we get an extra 2 hours after our presentation at the AIAA conference to present the teams that are just working so hard around the world, their concepts and ideas. So I was really excited to have that as well.
Yeah.
Okay, so exciting. Michael, I am not going to be coming within the next couple of months to South Africa, but definitely next year I will be in South Africa, and I'm super excited to get a chance to meet all these wonderful people and genius engineers and scientists from around the world coming together to actually solve a real world problem. So I'm so honored to be a part of this amazing team that we have. So thank you so much for all the time and effort you guys are putting into this project.
Yeah, thank you.
All right, well, great. Thank you again. And I guess we'll be back with the next webinar next week here in the US. It's Thanksgiving, so we're going to be skipping, and we'll have the Dutch team, and I can't wait to actually see your presentation or your team's presentation, Kamel, because I really want to see the videos. I know you guys posted a video already on your website of your trip to South Africa, but it will be great to hear from you guys firsthand your experience, and I think that would be very helpful for the rest of the teams, especially the ones that have not had an opportunity to be in South Africa, learn from your lessons. So thank you so much. I'm looking forward to it.
Yep, they're a great team.
All right. Thank you very much.
All right. Thanks, Steve, again, as always. And we're looking forward to seeing you in 2 weeks as well with the Dutch team. All right. Take care. Cheers.
Bye.
Cheers.
Bye.
Bye-bye. Thanks, Arend.